about these, what are these called? Epoxides. Okay, about this ring opening. Last class I didn't have a lot of time to explain this to you, but I feel bad, I can't live with this. So, I can't show you more because for the next semester you have that opportunity, okay? Now, attack can be here, and attack can be here, yes? Now, I had told you before, I told you last class that the attack was going to be here because this attack is faster, okay? Now, this attack is better under basic conditions, okay? And this attack is better under acidic conditions. So under basic conditions, here's the attack. Under acidic conditions, there is the attack, okay? Now, the reason why that happens is under acidic conditions, this oxygen here is protonated. And if it is protonated, what happens is that it opens up, and this here would be a secondary carbon. Yes? Secondary carbocation. Well, if it opens up this way, this will be a primary. But this is hindered by this group here, yes? So under acidic conditions, it attacks it here, and under basic conditions there. Now, what are acidic and what are basic conditions? Acidic conditions, anything that reads like this, yes? H+, okay? Maybe things like water and alcohol that are somewhat neutral will add to this side, okay? Under basic conditions are things that have, obviously, a negative charge. For example, this, which is what we did last class, yes? Yes or no? Now, we did something last class which was called a Grignard reagent. What is a Grignard reagent?
Magnesium, bromine, CH3.
Yeah, something like that, yes?
Yeah.
Something like
Magnesium.
magnesium and
Bromine.
bromine.
RMG.
And this is what type of compound? Is it nucleophilic? Is it electrophilic?
Nucleophilic.
It is nucleophilic. So this basically acts as if it were like this, yes? It's a nucleophile or a base. So what is that going to do? It is going to attack on which of those two sides? It is going to attack on the less hindered side. Yes or no? Okay? Under acidic conditions, on this side. Okay? Tell me, which one of those is less hindered?
You want to
Alkyl halide.
You want to write?
Less hindered.
left?
Left.
Left.
I mean,
Yeah.
you can see it with your own three eyes,
Yes,
yes?
no
Yeah.
kind of.
Look at it, and you go, an attack on this carbon here would be better than an attack on this carbon if it happens that way or if it happens this way. There is free rotation on those bonds there. Okay?
Yeah.
So, I don't know why this was a problem on the test, but this is better in SN2.
Yeah.
Yes, is that what you guys
Of
chose?
course.
Yeah.
They're all primary.
Yeah. But that has
But that was a
dangerous.
I
substitution.
changed it for the answer, so just shoot my other leg now, right?
Alright, so we're going to do something called now organocuprates. Okay?
Organocuprates.
Why do you have to organo? You know what an organ is? Organ, O,
Organic.
cuprates. So this is similar to the Grignard reagent, but instead of adding magnesium, we're going to have a lithium and we're going to add copper iodide. So first of all, we are going to have our
I was actually expecting that question on the test.
alkyl halide, but I said that wasn't going to be on the test, did I?
Yeah.
Really?
Did I say it was?
No, you said it wasn't.
Oh. How do you know?
The Grignard, did I say Grignard was gonna
No.
No.
Nope.
No.
I didn't ask.
I wrote one, and then I said, oh, maybe I didn't say it. Anyway, if we add lithium to this, what is a lithium going to do? As I explained to you in last class. Let's say it's going to add, let's say 2 lithium. What is it going to do? The lithium is a group 1 metal, and what do they like to do? They like to give electrons. Electrons to everybody, and if they give electrons to this, what does it form? It forms the lithium there, plus, because you guys like it this way, lithium bromide, which is of very little interest to me, because that's not the organic product. Okay? Now if you add copper iodide to that, you add copper iodide to this, you will form this organocuprate. And now, this lithium would, what does it look like? What type of, is it a nucleophile, electrophile?
Nucleophile.
Does lithium have a charge?
Plus.
Yes,
It is a metal, yes?
Yeah.
yes, electrified.
So it is kind of a plus. If you actually calculate the difference in electronegativity between this copper and that lithium, it's not ionic, okay? But it behaves like a nucleophile, so it behaves like an ionic compound. So what you are going to have is, you are going to have a copper here, and this is going to be 2 times. So I can say this copper like that twice. So what is going to happen is one side is going to have that chemical, on the other side, the other. So it will always have 2 of them. Yes or no? And they act like what? Like nucleophiles. And what do nucleophiles like to attack?
Electrophiles.
They like to attack electrophiles like what? Tell me. An example of an electrophile.
Something
Tell me the name of a compound that is an electrophile. Alkyl halide, yes?
Yeah.
Carbonyls, yes? Yes or no? How about this? It's an electrophile.
Electrophile.
So if you were to add this to this, what would it form? You write it down. You add this to this, and give me the product. So if I have this, I add this to it, two of these, then this lithium somewhere, what is it going to do? Are these conditions acidic or basic? Basic. How do you know they're basic? Because it's a nucleophile, that's right. Because it's a nucleophile, it's basic. And if it is basic, where is it going to attack?
On the right.
On this side. And if it attacks on this side, this opens to what side? This
Sure.
oxygen opens to that side. So it's going to look like this. The oxygen is going to be there, yes? And down here, you're gonna have this thing attached to it. This has, is this a carbon here? No, that is not a carbon, that is the bond to the carbon. It has 1, 2, and 3 carbons. Initially, this had 1, 2, and 3 carbons, yes? So I am going to put 1, 2, and 3 carbons, yes? Now, of course, under basic conditions, this is going to have a charge, but if you add water, or you add some acid, what is it going to do? It is going to get protonated. So eventually, it is going to look like that. What else can that attack? What else can it attack? Any electrophile, yes? I don't have to do all possible combinations. You might get some on the test you've never seen before. Did you get something today on the test you've never seen before? Like you've never seen sodium dichromate, right?
No, we've seen it. No,
You ever seen this before?
we've seen it. We've seen it.
You saw it on the test, right?
Yeah,
You
the
seen
same
it
thing
before
as
now.
promise.
No. Yet most of you noticed that this is what looked like you something you knew, yes?
Yeah.
And if you didn't know, and this would have been another element, you could see that 7 oxygens on this thing will probably make it
Oxidized, yeah.
So, let's say we have this. In the first step, we add lithium. In the second step, we add copper iodide. Let's say this is what's going to happen to you on the next couple of exams, okay? There's going to be a multi-step. Write both products.
And the problem you just erased, where, or I guess we can go over this one too, like, where does the CU and the Li, and the, like, how come we only added the carbon chain?
Because in this class, since it's organic chemistry, we only care about the organic product.
So CU and Li, they just leave?
Yeah, we're playing with each other. Copper positive and the lithium positive too.
Okay. So why do they just leave? They're both hanging out.
Hey, ask a mosquito about that. Why do male mosquitoes don't bite people?
I didn't know that.
Well, now
They
you know.
don't
Biology.
Male mosquitoes do not
Yeah, it's the
take blood
female.
from humans.
It's only the girls.
But I knew that because girls be taking blood from guys for a long time. I didn't have to.
Hey, that's the same thing I said when they thought about that topic.
So yeah,
Yeah.
I am drained. I only have blue blood.
Anything.
Damn. Okay, so what's the product? Once again, you don't have to see this, yes? Here's an alkyl halide. And you add lithium to it. What does it form? This
That with Li?
lithium, organolithium, yes?
Uh-huh.
And if you add this, it forms the organocuprate.
Yeah.
With two of
Times
them,
2, right?
right?
Yeah.
And then after this, what do you have here? This is an alkyl
Okay,
halide.
how
And what is this going to work as? This is
An electrophile.
Nucleophile,
or the
yeah.
electrophile. What is this?
It's an electrophile.
It's a nucleophile.
Nucleophile. It's a nucleophile.
Hold a second. Okay, let's do this one, okay? If
Alright.
you add these two things, what are you going to get? You are going to get the copper
Uh-huh. Times 2.
and the lithium and the iodide is everywhere. and you're gonna
Times
get
2?
two
Okay.
of these. The point is that this is going to be, what is this going to be?
The nucleophile.
That's gonna be the nucleophile. Can this be the nucleophile once
That's
again?
the electron.
Cannot be the nucleophile, okay? That has to be the electrophile, and alkyl halides are electrophiles. The point of this question here is that this is a double bond.
Bond, yeah.
If it would have been this,
That, then it would have been just,
then
okay.
it would have been easy for you. You would have said, okay, nucleophilic substitution here. It's SN2. Yes? SN2 or yes or no?
Yeah.
SN2, and it will give you 2 carbons more. Whatever you had, it added 2 carbons to it. But it's double bond now. So, how many carbons here? 1 and 2. I have this here. And where am I going to add the 1 and 2 carbons? I'm going to add it to 1 and 2 carbons. That's what happens. Double bond stays the same. What did you say? You're confused? You're not the only one. So organocuprates accomplish what type of bond making? Carbon-carbon bonds. So it is a way of elongating a chain. But what do you need before you can elongate the chain through organocuprates? You need an alkyl halide, then the lithium and the copper ion.
Okay.
What does the Grignard accomplish?
Same thing. I didn't.
It adds a C.
Alcohol makes alcohol.
It adds a CH3.
CH3 and alcohol. To prepare alcohol.
No, not all the time, it doesn't.
Elongation.
So tell me, how do I get this Grignard? I have, let's say, a BR. I want to make a Grignard from this. What do I add to this?
Mg.
What?
CH3.
CH3 and
MG?
G.
MG?
Doesn't it need an R group from the beginning?
R group?
Yeah.
What is that needs an R group? The MG?
Yeah.
No.
Oh no, it creates that R group plus the MG.
So what is going to happen is, now, if I put sodium here, what happens?
Sodium?
Yeah.
Nothing.
Sodium metal. What
Nothing.
happens?
Nothing?
Instead of Mg, I put sodium metal.
Oh.
What happens? It's going to donate the electrons. If I put lithium, what is the lithium going to do?
Donate the electrons.
to that. And if you put magnesium, what is it going to do?
Donate the electrons.
Just the same way. So what you are going to have is this MgBr. Once again, this is a nucleophile.
Nucleophile.
Yes?
Yes.
And nucleophiles attack what?
Electrophile.
Attacks an electrophile. Can it attack an epoxide? It attacks an epoxide. Can it attack an alkyl halide, like this one? Yes.
Yes.
And if it attacks an alkyl halide, what does it form? So let's say it attacks this alkyl halide. So what's the product to that?
Just gonna add that to that.
Write it.
See, okay, so you got this. This. Then GBR. Right?
So 1, 2, 3,
Uh-huh.
and
1,
2.
2. Yeah.
Okay?
Professor, so
Is it BR
is all of it a nucleophile or just the part with MGBR?
What do you mean MGBr? MGBr is positively charged, yes? Is that a nucleophile?
No, so when you say this is a nucleophile, what are you pointing to?
The carbon.
Oh,
This here. Yes. This is like this. And the Mg is positive. The Br is negative.
those
Is that supposed to be 5 or 6?
1, 2, 3. 1, 2.
1,
5.
2,
1,
3,
2, 3, 4, 5.
5. Okay. I know I ain't tripping.
Okay. Let's do 1, 2 versus 1, 4 addition.
And that's it, like, it doesn't have anything on the end? It's like that, fill out? I'm just asking.
It's weird, yes?
How do you
Okay.
know that?
1, 2 versus, what happened?
How do you know that they leave
How do you know that what leaves?
the BR? Like, how do you, like, from looking at it, how do you tell that? Like, how come it just doesn't get attached to it?
What gets attached to it?
The BR.
Attached to what?
Like, the end product, where is the BR?
She's asking the same thing
Here.
I'm asking.
Look.
Like, why is there no
But
There it is.
how do you, like, how are we supposed to know
On
that
what part
it?
is it detached? In the Granger, the VR staying. So I was just asking.
In the what?
In the Granger vehicle.
Ranger.
Danny Granger.
The VR staying.
The BR doesn't stay, guys.
It wasn't.
Okay, here's a nucleophile, yes? This is called the Grignard. It's a nucleophile. This is SN2. That's a leaving group. What the problem is? This carbon is now attached to that carbon. That's it.
Okay, so then what happens, so both the MG and the VR is.
So here you go. You want it? You want copper, bro? You have, what else do you want? You want lithium, sodium, magnesium, what else do you want?
Are we gonna do
Ice
mechanisms for
mechanism?
these?
We're not doing the mechanism, okay? We're doing 1, 2. The mechanism is, what is a mechanism? Look right there. What is it?
SN2.
SN2. How many times am I going to do SN2 mechanisms? With a what? Inversion of configuration. Okay, 1, 2 versus 1, 4. Now, there's something called the thermodynamic. Or thermodynamic control and kinetic control or product. Now, kinetic is about the speed, and thermodynamic control is about stability. Okay? So this happens for dienes. Is that a diene?
Yeah.
That is a diene. This is 1, this is 2, 3, and 4. Yes or no? Now, if to this diene I add, let's say HBr. We're not continue doing mechanisms for this because you are supposed to already know these mechanisms. And if I add HBr to a double bond, what happens? 1 H goes to one side, the Br goes to the other side. According to whose rule? Markovnikov. This is Markovnikov addition. Why is it Markovnikov addition? Because I said so. Because it's the formation of a carbocation. So this is what happens. Here's a double bond, yes? 1 H adds to this side. I did not draw the rest of the H's, okay? I just drew this H. And the Br goes to the positive, yes or no? Hello? So it is a possibility that the Br minus from this HBr attacks this, and the product that you get is H here and Br here. Now, was that 1, 2 addition or was it 1, 4 addition?
1, 4.
1, 2.
You sure?
1, 4.
Because some of you will be confused and you say, no, that was 3, 4. It doesn't matter if it's 3, 4. It's still 1, 2.
1, 2.
To one carbon and then to the other carbon. The one next to it. So this is called 1, 2 addition.
Okay.
I'm surprised. You did not complain this is 3, 4 addition.
Oh.
So that's 1, 2 addition. You got the mechanism for this? Now, if you are here, can there be a resonance for this?
Yeah.
What type of carbocation is that?
Secondary?
Secondary?
No.
That's a better name.
Diallylic.
It is an allylic
It's allylic
carbocation.
'cause
It is
it's,
secondary, and it is allylic.
Secondary allylic carbocation?
Okay, so what happens is, double bond goes there. And when the double bond goes there, what we get is, check if you can follow that.
That's really.
Professor, thermodynamic and kinetic.
Kinetic
are they
is speed, right?
corresponding to 1, 2, and 1, 4, or?
Yes, just listen to this for a minute, okay? Let me finish. So you can ask about something I wrote 25 minutes ago. Guys, are you happy with this resonance structure that I drew here?
Yes.
The double bond went here, and the positive charge moved to this carbon here. Yes or no?
Yes.
Yeah.
Now, is there a possibility that one of the Br minus is going to go there and attack there? Yes. If it does attack there, what you form is this. The hydrogen was here, and now the bromine is here.
Yeah.
Okay, so this addition was what?
1, 4.
This was 1, 4. Now, it doesn't matter if I label this 4 before or 1. 1 was added to this position, and the other one was added 4 carbons away. Yes? 1, 2, 3, 4. So, one was added here, the other one was added here.
Mm-hmm.
Versus one was added here and the other one here, or one here and the other one there.
Okay.
Is that clear?
Yeah,
1, 2 versus 1, 4. Now, which one of those two is more stable to you?
yeah.
Is this
1, 4?
more stable?
Yes.
Oh, wait.
Yeah.
I didn't draw this double bond here, did I?
That was
Yeah.
You were gonna say, but you never said it, because you didn't want to be annoying, right?
exactly.
Good job. Step.
So 1, 4, more stable.
So, which one is more stable, this one or this one?
That one, 1, 4.
This one is more stable. Why is this more stable?
Because I substituted.
You guys take my breath away. This is disubstituted. So this is more stable. And because this is more stable, what type of product is this?
Major. Oh,
Thermodynamic.
thermodynamic, okay.
So this is the thermodynamic product.
Oh, yeah, because it has to do with stability. Ah.
Now, the kinetic product is the one that happens fast.
Fastest, right?
So, this is the one that happens fast. Why does it happen fast? Well, it adds hydrogen here, and immediately what happens?
The BR.
The Br goes there. It doesn't give it time to do this resonance structure. So, when do you get the thermodynamic versus the kinetic? You get the kinetic at low temperatures, and you get the thermodynamic at high temperatures. Now, that's a little bit weird, yes? Now, when I was a kid and I heard this, I said, that doesn't make sense, yes? But at low temperatures, everything is happening slower. So this is happening slower. At high temperatures, you always get side-step rule, yes?
Wait.
Because you're slowing down the reaction so much that the 1,4 doesn't take place. It's 1,2. Low temperatures, 1,2. High temperatures, 1,4.
And kinetic favors low temperature.
1,2 is kinetic, 1,4 is thermodynamic. What do you get at low temperature, guys? 1,2 or 1,4?
1, 2.
1, 2.
Kinetic or thermodynamic?
Kinetic.
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 So is that kinetic? Wait, which one did you say was kinetic? I'm sorry, you were going so fast.
No, that's okay. I can tell you again, okay?
No, I was just
This is
asking.
thermodynamic, 1,4.
Exactly.
1,4 is thermodynamic. High temperatures. Okay? 1,2 addition is kinetic control. And what else? Low temperatures. So we're gonna do Diels Alder now. Diels who?
Diels Alder. Diels Alder.
By the way, these organocuprates is called Gilman.
Gilman. Organic Coupate.
Yeah, this was on the test. This is called Gilman.
Gilman.
Yeah, I put it on the test, but you guys did not have a clue. You're like, who's Gilman?
That was what he asked me.
Okay, let's do, we are going to do the cycloadditions that you guys did in the lab, yes?
Oh, I didn't even look at that.
What happened? Now that stuff is called,
What?
look, we got choices. Diene and dienophile.
Yeah.
Which one is it, diene?
The right one.
Di-2-enes, yes? And this is the dienophile. This is attracting this thing. This has to be in the S-cis conformation. What that means is it has to look like this. It cannot look like that. Okay? This is called trans. This is S-cis. Now what happens is these two electrons from this double bond are going to make a new bond between this carbon and this carbon. You see it? These two are going to make a bond here. Now this double bond is going to make a bond here because now it doesn't need it since these electrons are going to make a new bond here. And now these two are going to make a bond between this carbon and that carbon. It's called a cycloaddition. And what do you get from this diene and dienophile? Cyclohexane. So you don't have to spend so much time thinking about this stuff, you know? You just do whatever you want to do here. Some people say clockwise, some people say counterclock. You can do whatever you want. Okay? It doesn't make a difference. But it's going to give you at the end, it's going to give you that.
A double bond in the
So let's say I have this.
You're missing a double bond.
Oh yeah. So give me the products for that. And while you're at it, let's say it's supposed to be electron withdrawing groups. Huh?
I just learned it a different way. I don't know.
You learned it in a different way?
Yeah.
What way was that?
Break the double bond.
You break the double, like, okay,
and add
so
it to
you,
2 and 3.
yeah, so it's like the diene will have 1, 2, 3, 4. You break those 2 bonds, and you break that middle bond, and then one is gonna attach to 6, and
Just
four is
do it
gonna
the way
attach to
you
5,
learn it.
and you just,
Same thing.
and
Just
2
do it
and 3 will make a double bond.
Really the way you learn it.
Just do the way you do it.
Because you use the word break,
I don't know.
that's why it's different?
I
If it
don't,
was closed, then
I don't know. It looks like a soccer ball to me.
No numbering, no carbon. This is not kindergarten, this is organic chemistry, my friends.
Yes, I know. It just
There's no babysitting
You
anymore.
can so when we first started, they were kind of facing each other. This one we can.
So we're
Oh wait,
kind of facing each
never
other.
mind. Never mind.
They're still facing each other. So we are going to, she said break the double bond, yes? We broke it. Let's break this other one. And let's break this one too. We break everybody. What do we get?
You get an attachment.
This,
With a double
the double
bond
bond goes here
and
in
a
the
CN
back.
coming out.
With
And then
attachments.
this CN goes here.
That's it.
Okay, you like that? What's the problem?
No problem.
on the opposite side. I mean, like on the right. Wait, you can't do that.
You put it here
Yeah, you can't do
and the
that.
CN here,
Yeah.
that's fine.
Okay.
If you drew this the other way, it's fine. I don't care. It's the same thing.
Yeah, that's what I was saying about facing the other way.
Yeah, it's the same thing, guys. If there is a double bond and the CN is in the place where it's supposed to be, it's fine. So, what happens here? This is serious problem, yes?
No, you just end up with.
You just end up with two double bonds.
So, that one goes there. What would you like to call that? Like to call that breaks? This one has to go here. And that one goes there. Cyclohexane, yes? Double bond goes here. We only use one pi bond from here. So there's another double bond there. And there is a CN here and a CN there. Huh? Cyclohexadiene. It's still a diene. Okay guys, we're almost done.
Right? But I understand what that's the problem.
Yeah.
Yeah, 1, 2, 3.
Let's not draw this like this. So, okay, ready? Now, is this difficult? Is this
No.
one difficult?
How did
No.
it connect?
No? It's not.
You
Okay.
first break.
Now, this is a diene, yes?
Yeah.
And this is a dienophile. The answer is going to be what?
Break.
Cyclohexane, right? This is going to make a bond there. That one is going to make one there, and this one here. I drew this differently from the other one, so you don't get used to one thing. It's still a cyclohexene. There is a double bond here, yes or no? This are those two carbons, yes or no?
Yep.
So this one is going to have here this stuff on it, yes or no? Yes or no?
Yep.
Now the only difference is these two carbons
It's gonna make it easy.
are these two carbons, yes or no? And these two carbons have a triangle in it, right? It has CH2 and bridge to the other one. So all you have to do is just like that. Because of the triangle? Yes. So whatever is inside of this thing, that's what you are going to draw inside. You want another one?
Can you go
Hello?
over the bridge again?
Oh my gosh.
Did I what?
Can you go over the bridge again?
What do you mean over? Why I drew the bridge?
I don't understand yet.
This is this cyclic compound, right? It doesn't break. This carbon here is this carbon. And this carbon is that carbon. It has, between these two carbons, it has a CH2 attached to these two.
Oh, okay.
So there it is. You see it?
Yeah.
That's what that was, it's 5-member ring.
Oh, Professor, don't you do that?
Everybody draw it. I don't want you staring at the board. So I imagine you were just doing nothing. Fake it until you make it, yes? Write your boyfriend's name down, so I imagine you are trying the problem I have given to you. So, cyclohexane, yes or no?
Yeah.
Yes.
Yes, there is a double bond that goes on this side, and there is a CN that goes here. Is that it?
Nope,
No.
at all.
This here, now instead of having a triangle, what does it have now? It has these two things. I'm going to go inside of this, and I'm going to draw it. Right, that was not pretty enough for you, was it?
No.
You like that better?
What if you draw it like this? Professor, let me,
Did you say, what is that?
Professor, can I show you something? What if you do it like this? Is it,
Huh?
what if you do it like this? Is it okay? No?
No, that is not okay. That's zigzag.
What did you do?
No, it's okay, but it's not. Okay,
Professor, how come the bridge is made by the top of the bond and not by the bottom?
I know, that's how I did.
Like, so the bottom triple bond, you move it up, right? It doesn't go.
I don't understand what moved up.
That one, they moved up, right? You draw the arrow in that one?
You mean you want that? Is what you say?
Right, so,
No, it could be this. It doesn't matter what it did. But one is going to do that while the other one does the other stuff. Okay, if you notice, the good thing to put on the dieno file are electron withdrawing groups. And this is going to be very important when you take organic 1 and you do electrophilic aromatic
Organic
substitution.
one?
2?
I don't know, I thought it was dyslexic because I didn't understand what you were saying.
You are dyslexic because I said organic 2.
I figured.
You're blind.
It's okay.
So,
What things have to do with another?
guys, why are you talking so much? Damn. This is electron withdrawing groups, while these groups here are electron releasing groups or electron donating groups. So, I don't know what you want to call it, electron donating groups are the good groups to put in a dieno file. And the good groups to put on a no, I said it the other way. What's it called?
Are you dyslexic? Isn't that my fault?
Electron withdrawing groups are those like they have an element, and next to that element they will have electronegative elements. So they will have, here's a carbon, and what is this carbon here? Is it delta positive or delta negative?
Delta positive.
Delta positive, because this is withdrawing electron density from here, and so is this one.
Right.
And this one here, what is it?
Negative.
Delta positive again,
Positive.
because this is more electronegative than that. How about NO2?
The
There is a
end.
nitrogen, but next to the nitrogen, you have these oxygens that are pulling electron density away from it. So everything with a carbonyl, it's electron withdrawing. Okay? Now, anything with a CH3 or any type of alkane is electron donating. So things like CH3 are electron donating. Things like halogens are electron donating. Okay? Things with an oxygen are electron donating too. I think that's it. You want to see the approach or no?
Yeah.
yeah. But you're not gonna do that.
See what?
I'm not gonna do what?
The approach.
So for example, I'll ask you on the test. I'll ask you on the test. Which one
Everybody woke up now.
which one is a better dienophile? Dienophile, no, diene.
Dang.
Which one is better? The one with the CN or
Which
the
is
one with the
better what?
methyl group? Diene. Look at it.
CH3.
CH3.
Which one is a better diene?
CH3.
This one is a better diene because it has an electron donating group attached to it. Okay? Which one is a better dienophile?
CN.
The one with a C. Okay? Now, the approach for this thing, okay, I have done it this way, but the approach is from either the bottom or from the top. Some people draw this thing like this. Like saying it's going to make a bond here, it's going to make a bond there. You ever seen that before?
Yeah.
Let's see if I can draw
My
this.
car. I remember.
So if this is cyclopentene, yes? Pentadiene, the double bond is going to approach it from the same side, okay? Or the dienophile is going to approach it from the same side, okay? So that's just the approach. I don't want to talk about more. We're a little bit behind schedule.